In this video, we're computing a definite integral of this big rational function, and this problem is a classic partial fractions decomposition integral. So what we do is make a partial fractions decomposition proposal for our integrand and break it into smaller pieces. So we're going to say, let's propose that this huge rational function, 3x squared plus x plus 1 over x squared plus 1 times x minus 2, can be written as a sum of two simpler fractions, each one of them having one factor from the denominator. So I'll start with the irreducible quadratic factor. And the most general proposal here is to say, well, maybe it has a linear numerator. So we write that as ax plus b, and the denominator there is x squared plus 1. And then we make our proposal for the linear factor. So we have a c over x minus 2. The next step here is to multiply both sides by the least common denominator, which is just the product of these original factors in the denominator. And when we distribute these factors to the left-hand side, just the numerator is left. So we have 3x squared plus x plus 1 on the left-hand side. And on the right-hand side, when we distribute these factors to our first term, the quadratic factor is going to cancel out, leaving us with just the numerator, ax plus b, multiplying x minus 2. And a similar cancellation happens on our linear term. That x minus 2 cancels out, leaving us with a c times x squared plus 1. So now we're looking at an equation that has three unknowns in it. That's a, b, and c. And it has to be true for all values of x. And this gives us a lot of flexibility in our solution technique. I can sub in any value of x that I want, and that'll give me a relationship between the a, b, and c. I can also compare coefficients of the different powers of x on the left and right sides to find relationships between a, b, and c. So I'm going to take a hybrid approach here because the low-hanging fruit is a substitution, x equals 2. If I sub that in on the left side, I get 3 times 4, which is 12, plus 2, that's 14, plus 1, so 15 total on the left-hand side. And making that substitution wipes out this ax plus b times x minus 2 term. And all I'm left with is a c times 2 squared plus 1, or 5c. So the substitution method immediately gets us c, and it turns out that c is equal to 3. After that, I'm going to use the comparing coefficients of different powers of x method. So I'm going to look at the coefficients of x squared on the left and right hand sides. And on the left, that's a 3. And then I go through and look for every term that's quadratic on the right hand side. Well, I can get an ax squared from this product, ax times x. And that's the only quadratic term that comes out of that product of binomials. So I end up with an a times x squared. In other words, the coefficient of x squared there is just a. And then I also have a c times x squared. So the coefficient of x squared on the right-hand side is a plus c. Well, given that I already know what c is, I quickly find a. Since c is 3, a must be 0. So I'll just go to the linear term next. The coefficient of x on the left-hand side is 1. And on the right-hand side, I see a linear term when I multiply ax times negative 2. So I have negative 2a. And then I get another linear term when I'm distributing across these two binomials, and that's bx. So my coefficient of x there is plus b. And the c-containing term doesn't have any linear pieces at all. Now we already know a is 0, so now we find that b is 1. So we have a, b, and c. And that means we can now decompose our original big rational expression into these two simpler rational expressions. So our original integral becomes the integral from 0 to 1 of our first piece, ax plus b over x squared plus 1. Well, we found out a was 0 and b is 1, so that piece is just 1 over x squared plus 1. Then we have a c over x minus 2, but c is 3, so I have 3 over x minus 2. And the whole point of partial fractions decomposition is that the antiderivatives of these smaller pieces are generally pretty easy to find. So the first piece just integrates to the inverse tangent function, and I end up with inverse tangent of x evaluated from 0 to 1. And the second piece integrates to a natural log function. So I have 3 natural log absolute value x minus 2 evaluated from 0 to 1. Now we just have to do these evaluations. So when I sub in the upper limit on the inverse tangent part, that gives me an inverse tangent of 1. In other words, the angle whose tangent is 1, and that's just pi over 4. Then I subtract from that the angle whose tangent is 0, which is just 0. Moving on to the natural log piece, when I sub in the upper limit, I end up with 3 natural log absolute value of negative 1 but that's an absolute value there, so it's 3 natural log of 1. Well, the natural log of 1 is 0, so I get a 0 out of that. And then I subtract 3 natural log absolute value of 0 minus 2, but the absolute value of negative 2 is just 2. So I end up with a negative 3 natural log 2 there. And we clean things up just a little bit. I have pi over 4 minus 3 natural log 2. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zax Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zax Lab, and best of luck on your math and physics journey.